Imagine standing on the edge of a vast, endless ocean at night. The water stretches out forever, black and silent, reflecting a sky full of stars. You hold a stone in your hand, smooth, heavy, perfect for skipping across the surface. You wind up and throw it with all your strength. The stone skims once, twice, 3 times, sending out perfect circles of ripples that spread and fade into the darkness. Now picture throwing that same stone with 10 times the force, 20 times, 100 times. No matter how hard you throw, the ripples never travel faster than a certain quiet speed across the water. The stone might skip farther, might send out bigger waves, but the speed of those waves remains exactly the same, calm, steady, unbreakable. That quiet limit is the universe speaking to you in its simplest voice. We live in a cosmos that has drawn a line no one can cross. Not rockets, not particles, not information, not dreams. There is a speed beyond which nothing, absolutely nothing, can go. We call it the speed of light, but it is more than a number. It is a boundary woven into the very fabric of reality. And here is the part that should stop you in your tracks. This boundary does not exist because we lack clever enough engines or powerful enough fuel. It exists because if anything ever crossed it, cause and effect would reverse, time would lose its arrow, and the difference between past and future would collapse like a house of cards. The stars you see tonight are not just far away. They are imprisoned. We are imprisoned with them. Every planet, every galaxy, every possible home for life is locked behind walls of distance that this speed limit makes effectively infinite for anything made of matter. What if every story humanity has ever told itself about reaching the stars, about spreading across the galaxy, meeting other minds, escaping the fate of our sun, is not merely difficult but forbidden by the deepest laws of existence? What if the universe, for reasons we may never fully grasp, has chosen isolation as the fundamental condition of life? Tonight, we are going to follow the chain of evidence that forced scientists to accept this cosmic prohibition. We will start with observations so ordinary they feel like common sense, then watch as those observations lead us step by step into territory that feels increasingly alien, increasingly unsettling. Along the way, we will meet experiments that refuse to behave the way every previous generation expected. We will watch brilliant minds wrestle with results that seem to mock everything they thought they knew about reality. And by the time we reach the end, you will understand why the speed of light is not just a speed. It is the guardian of causality itself, the silent rule that keeps the universe coherent, keeps yesterday before today, keeps effects following causes. This is not a story about what we might achieve someday with better technology. This is a story about what the universe simply will not allow, no matter how clever we become. Prepare yourself. The journey begins gently, with ideas that feel familiar and safe. But it will carry us farther and farther from everyday intuition until we stand at the edge of concepts that make the mind real. We begin in the late 19th century, when physics felt complete, almost tidy. Scientists believed they had mapped out the basic rules governing motion, electricity, magnetism, and light. The picture was elegant. Light was understood as a wave like sound, like water ripples, traveling through a medium that filled all of space. They called this invisible medium the luminiferous ether. It was the quiet ocean through which light waves moved, just as sound moves through air. Because Earth is racing around the sun, physicists reasoned, we must be moving through this ether at considerable speed. And if we are moving through the medium that carries light, then the measured speed of light should change depending on direction, faster when we move with the current of the ether, slower when we move against it. It seemed obvious. Everyone expected to detect this difference. Measuring it would even tell us how fast Earth was moving through the absolute rest frame of the universe. The experiment promised to reveal the one true motionless backdrop against which all motion could be judged. 2 American scientists, Albert Michelson and Edward Morley, built an instrument of extraordinary precision to catch this tiny effect. Their device split a beam of light, sent the 2 halves along perpendicular paths, reflected them back with mirrors, and recombined them. If the ether existed and Earth was moving through it, one beam would take slightly longer to complete its journey than the other. When the beams reunited, they would be slightly out of step, creating an interference pattern, bright and dark bands, that would shift depending on the direction the instrument faced. They expected a small but clear signal. They found nothing. Season after season, orientation after orientation, the interference pattern remained perfectly steady. The 2 beams always arrived back together, as if Earth were perfectly still, or as if the ether did not exist at all. The result was so clean, so stubborn, that it became one of the most famous null results in scientific history. Physicists tried to explain it away. Perhaps the ether was dragged along by Earth. Perhaps lengths contracted in the direction of motion to hide the effect. The explanations grew elaborate, almost baroque, as scientists struggled to preserve the comfortable picture they had built. But the data refused to budge. Light's speed appeared to be the same in every direction, for every observer, no matter how the observer was moving. This single, simple fact sat at the center of physics like an unmovable obstacle. Then a young patent clerk in Switzerland, working far from the great universities, took the result at face value. Albert Einstein asked himself what the world would have to be like if the speed of light really was the same for everyone always, without exception. He began with a thought experiment that feels almost playful at first. Imagine chasing a beam of light. You run faster and faster, closer and closer to its speed. What do you see? Common sense says the light should appear to slow down ahead of you, like a car you are catching up to on the highway. The distance between you and the light beam should shrink, and its relative speed should approach zero. But the Michelson-Morley experiment, and every measurement ever made, says that no matter how fast you move, the light continues racing away from you at its full, unchanged speed. Einstein realized that the only way to make this true is if space and time themselves adjust to protect the constancy of light's speed. Clocks must run slower for moving observers. Rulers must contract in the direction of motion. Events that appear simultaneous to one person must happen at different times for another moving past them. These are not optical illusions. They are not tricks of perception. They are real physical changes in how space and time behave. At everyday speeds, the effects are far too small to notice. That is why our intuition feels so certain, so reliable. But push close to the speed of light, and the universe begins to stretch and bend in ways that defy imagination. Einstein published his ideas in 1905. Most physicists greeted them with skepticism, even ridicule. Time-changing rate, length shrinking, simultaneity depending on motion. It sounded like philosophical nonsense dressed up as physics. But then the predictions began to be tested. Particles accelerated in laboratories behaved exactly as the theory predicted. Clocks flown around the world on airplanes ticked at slightly different rates depending on their speed and altitude. Atomic clocks on fast-moving satellites had to be adjusted precisely according to Einstein's formulas for GPS to work correctly. Every test confirmed the same thing. The speed of light is not just a limit for light. It is the universal speed limit for everything, matter, energy, information. And the closer anything with mass gets to that limit, the more energy it takes to push it even a tiny bit faster. The curve is not linear. It rises gently at first, then steeper and steeper, approaching vertical as you near the forbidden speed. To reach it exactly would require infinite energy. To exceed it is not merely impractical, it is undefined. The equations simply stop making sense. Imagine trying to walk up a hill that gets steeper with every step until the ground in front of you becomes a sheer vertical wall. You can get arbitrarily close, but the wall is absolute. That wall is the speed of light. This is where the story begins to feel less like triumph and more like cosmic solitude. Because once you accept this limit, the universe suddenly becomes vastly larger in practical terms than it appeared before. Distances that seemed challenging now become insurmountable for anything made of matter. A journey that would take light itself years to complete would take a material ship vastly longer, not because of fuel or engineering, but because time itself stretches for the travelers, while centuries or millennia pass back home. And even for the travelers, there is a hard boundary. No matter how long they are willing to spend accelerating, they can never shorten the trip below the time light itself would take. The stars remain forever out of reach in any timescale that feels human. This is not speculation. This is the direct consequence of the evidence that began with a quiet experiment in a basement laboratory and led, step by reluctant step, to a complete rewriting of space and time. We have only begun to scratch the surface. In the parts to come, we will explore how this limit shapes the behavior of particles in accelerators, how it explains the impossible brightness of distant quasars, how it forces black holes to hide their interiors from the universe forever. We will see why causality, the simple idea that causes precede effects, depends absolutely on this boundary remaining unbroken. And we will confront the deepest implication of all, that the universe may be designed, or may simply have evolved, in such a way that intelligent life is forever scattered, forever alone, separated by gulfs not merely of distance, but of unbreakable law. The evidence is overwhelming. The conclusion is humbling. Our journey has only just started. We left off at the edge of a revelation that changed everything. The speed of light is not just constant, it is the unbreakable ceiling for all motion in the universe. And to protect that constancy, space and time themselves must bend and stretch in ways that feel deeply unnatural to us. Let us explore what this actually means in practice, not through equations or technical jargon, but through stories and pictures that bring the strangeness alive. Imagine two friends, Anna and Alex. They grew up together on Earth, inseparable. One day, Anna decides to take a journey. She boards a spacecraft that accelerates smoothly, day after day, year after year, getting closer and closer to the speed of light. Alex stays home, watching the ship disappear into the stars. From Alex's perspective on Earth, something extraordinary happens to Anna's ship. As it approaches that forbidden speed, time on board begins to slow down. A clock that ticks once per second for Alex might tick only once every 2 seconds for Anna, then once every 10 seconds, then slower still. Years pass for Alex while only months slip by for Anna. But here is the part that twists the mind. Anna does not feel anything unusual. Inside her ship, her clock ticks normally. Her coffee cools at the usual rate. Her heartbeat feels steady. She looks in the mirror and sees herself aging at the ordinary pace. When she looks back at Earth through a powerful telescope, it is Alex's world that appears to be rushing forward in time. She sees seasons flashing by, cities changing, Alex growing older far faster than she does. This is not an illusion. This is not science fiction. This is time dilation, the real measured stretching of time for moving objects. Now imagine Anna turns the ship around after a long journey and returns home. From her point of view, the round trip took perhaps a decade. She steps off the ship expecting to find Alex roughly the same age, maybe a little grayer. Instead, she finds Alex old, or perhaps even gone. Decades, maybe centuries, have passed on Earth while only years passed for her. This is the twin paradox, one of the most famous thought experiments in physics. The traveling twin returns biologically younger than the stay-at-home twin. The paradox seems to appear because motion is relative. Why does only the traveler experience the slowdown? The resolution lies in the fact that Anna's journey involved acceleration. Turning around requires changing direction, which breaks the symmetry. But the deeper truth is that time itself flows differently depending on motion through space. We have seen this effect in the real world, not just in imagination. Consider particles called muons. These are created high in Earth's atmosphere when cosmic rays strike air molecules. Muons are unstable. They decay into other particles after an extremely short lifetime, too short for them to reach the ground if they traveled at ordinary speeds. Yet detectors on mountaintops and deep underground record showers of muons arriving constantly. How do they survive the journey? From our perspective on Earth, the muons are moving so close to the speed of light that their internal clocks run dramatically slower. What feels like a brief moment to the muon stretches long enough for it to cross the entire atmosphere before decaying. From the muon's perspective, the distance through the atmosphere shrinks dramatically, length contraction in action. The journey that seems vast to us becomes a short hop for the speeding particle. Both views are correct. Both effects are real. Another everyday confirmation sits in your pocket right now. The global positioning system, those satellites that guide your car or phone, must account for both the slowing of time due to their high speed and the speeding up of time due to their weaker gravitational field. Without precise corrections based on relativity, the system would drift by miles every day. Clocks on the satellites tick at a different rate than identical clocks on Earth. Engineers adjust for this difference down to the tiniest fraction. The fact that your navigation works is quiet proof that time really does flow differently for moving objects. These effects, time dilation, length contraction, are not optional interpretations. They are forced upon us by the constancy of light's speed. But there is another consequence that makes the speed limit feel even more absolute. As an object with mass accelerates closer to the speed of light, it becomes harder and harder to push it faster. The resistance grows without bound. Imagine pushing a child on a swing. At first, a gentle nudge sends her soaring, but picture trying to push a massive boulder on that same swing. Each additional bit of speed requires vastly more effort. Now imagine the boulder getting heavier the faster it moves. The faster you push, the more its effective mass increases. Near the speed of light, that mass becomes essentially infinite. To give it even the tiniest additional speed would require infinite energy. This is why no material object can reach the speed of light, let alone exceed it. The universe does not run out of fuel. It simply makes the object infinitely heavy in terms of the energy needed to accelerate it further. Particles and accelerators around the world demonstrate this daily. Scientists smash protons together at speeds so close to light that the difference is smaller than any everyday comparison. Yet no matter how powerful the machine, no matter how many stages of acceleration, the particles never quite reach that final boundary. They approach it asymptotically, forever closer but never there. The energy poured into these machines is staggering enough to power cities, yet it only buys tiny increments of speed near the limit. Light itself, photons, have no rest mass. They are born at the speed of light and live their entire existence there. They do not accelerate, they simply exist at the boundary from the moment they are emitted. Anything with mass, however, atoms, molecules, people, planets, is forever barred. This barrier has profound consequences for our dreams of space travel. Consider a journey to the nearest star. Light itself takes years to arrive. A ship traveling at, say, half the speed of light would take roughly twice as long from Earth's perspective. But thanks to time dilation, the crew might experience only a fraction of that time. Push closer to the limit, say, a speed so close that the difference is negligible, and the crew's experience time shrinks dramatically. A journey that takes light years might feel like only months to those on board. There is a catch, however. Accelerating to that speed and decelerating at the destination requires enormous energy and time. The ship cannot simply jump to near light speed instantly. The acceleration must be gentle enough for humans to survive, stretching the process over years. Even then, the return trip presents the same problem in reverse. And while the travelers might age only decades, centuries, or millennia pass back home, the stars become reachable in principle for the brave crew willing to leave everything behind forever. But colonies, regular trade, cultural exchange between worlds, those remain impossible. The time debt is too great. And no amount of future technology can erase this debt, because it is not technological. It is woven into spacetime itself. This is where the story begins to feel less like a puzzle solved and more like a cosmic sentence handed down, because the same rule that prevents faster-than-light travel also prevents sending information faster than light. No signal, no message, no radio wave can outrun light. If a colony were somehow established on a distant world, it would be cut off from Earth not just by distance, but by time. Messages would take years or centuries to cross the gulf. Events on one world would remain unknown to the other for generations. The galaxy becomes a collection of isolated islands, each evolving in solitude. Some have wondered whether exotic solutions exist, wormholes that shortcut space, or warp drives that move space itself around the ship. These ideas appear in theoretical physics, but they require forms of energy or matter that may not exist, or that would destabilize catastrophically if they did. Even if possible, many physicists argue they would still violate the spirit of causality, allowing effects to precede causes in some frames of reference. Because the deepest reason for the speed limit is the preservation of cause and effect. Imagine sending a message faster than light. In some moving frames of reference, the message would arrive before it was sent. The reply could arrive before the original question. Paradoxes multiply. You could receive instructions to prevent the message from ever being sent. Time travel paradoxes, grandfather paradoxes, all become possible if causality is violated. The universe appears to have chosen consistency over connectivity. It prioritizes a coherent timeline where causes always precede effects, even if the price is eternal separation. This is the accumulated evidence speaking through a century of experiments and observations. From the quiet basement where Michelson and Morley found no trace of the ether, to the particle trails in cloud chambers showing time-stretched decays, to the precise orbits of satellites confirming clocks run differently in motion. Every test has confirmed the same picture. Every attempt to find a loophole has failed. We are left with a universe that permits motion up to an absolute boundary and forbids anything beyond. The question now shifts from how do we go faster, to why does the universe enforce this isolation? Is it mere accident, a consequence of how physical constants settled after the Big Bang, or does it serve some deeper purpose we cannot yet glimpse? As we continue this journey, we will explore how this limit shapes the largest structures in the cosmos, black holes that trap even light, horizons beyond which no information escapes. We will see how it influences the earliest moments of the universe, when everything was closer than it is now, yet still bound by the same rule. And we will confront the possibility that intelligence itself may be rare not because life is hard to start, but because the speed limit makes the galaxy effectively infinite for any species bound by matter. The evidence builds, layer by layer, toward a picture both majestic and melancholic. A universe vast beyond comprehension, filled with wonders we can see but never touch. Our exploration continues. We have seen how the constancy of light's speed forces time to stretch, distances to shrink, and masses to swell toward infinity as we approach the forbidden boundary. These are not distant theoretical curiosities. They are happening right now, in the atmosphere above our heads, in the circuits of the devices we carry, in the accelerators buried beneath the Earth. But the story grows stranger still, because this speed limit does not merely restrict how fast we can travel. It shapes the most violent and extreme places in the cosmos, places where gravity itself becomes so intense that even light struggles to escape. Imagine standing on a perfectly ordinary world, much like Earth. The sun rises and sets, the wind moves through trees, life feels stable, predictable. Now picture that world slowly collapsing inward, its entire mass squeezing down into a smaller and smaller sphere. As it shrinks, gravity on the surface grows stronger. At first, you would barely notice, perhaps objects feel a little heavier, but as the collapse continues, the pull becomes crushing. Escaping the surface requires more and more speed. There comes a point where the speed needed to break free equals the speed of light itself. Beyond that point, nothing, not light, not rockets, not screams, can climb out of the gravitational well. The surface becomes a horizon, a one-way boundary. Anything that crosses it from the outside falls inward forever, vanishing from the rest of the universe. Anything already inside can never send a message outward. This is a black hole. The idea sounds like nightmare or fantasy, yet it emerges directly from combining the rules of relativity with the simple fact that gravity exists. The mathematics is unforgiving. Once a certain density is reached, collapse becomes inevitable, and the horizon forms like an absolute prison. Light skimming the edge of this horizon bends dramatically, stretching around the curve before escaping. Light that falls just short circles forever in a fragile orbit, a photon sphere where beams of light can loop endlessly without falling in or flying away. From far away, the approach to the horizon appears to take infinite time. An object falling toward it seems to slow down more and more, its light reddening and fading as time dilation stretches the final moments into eternity. The falling object itself, however, experiences no such pause. It crosses the horizon smoothly and continues inward to whatever awaits at the center. No one outside ever sees the crossing. The horizon freezes the last image of the falling object forever, a ghostly silhouette etched against the darkness. Black holes are not theoretical curiosities. We have watched stars orbit invisible companions whose gravity is far too strong for anything but a black hole. We have seen gas clouds spiraling inward, heating to incandescent temperatures as they plunge toward the horizon, releasing bursts of energy brighter than entire galaxies. We have even captured the shadow of a black hole itself, a dark circle surrounded by a glowing ring of trapped light, exactly as relativity predicted. These objects are the universe's most dramatic demonstration that the speed of light is not just a limit for travelers. It is the boundary between what can be known and what is forever hidden, because once something crosses the horizon, no information about it can ever reach the outside universe. The interior becomes causally disconnected from everything else. What happens inside stays inside, shielded by the same speed limit that protects causality everywhere else. This disconnection feels almost deliberate. The universe permits extremes of density and gravity, but it draws an impenetrable veil around the consequences. And black holes are not rare. They form from the deaths of massive stars. They lurk at the centers of most galaxies, including our own, a supermassive beast quietly orbiting in the Milky Way's heart, its influence felt in the frantic dance of stars around an empty point in space. These monsters grow by devouring matter, merging with one another in collisions that send ripples through spacetime itself, gravitational waves we now detect with instruments of exquisite sensitivity. Every observation confirms the same picture. The speed of light rules even in the most extreme conditions. Gravity can bend it, slow its escape, trap it entirely, but never ever make it go faster. This brings us to an even deeper layer of the mystery. Consider the earliest moments of the universe, just after the Big Bang. Everything, all matter, all energy, all space itself, was compressed into a region of unimaginable density and heat. In that era, the entire observable cosmos was smaller than a grain of sand, yet already expanding rapidly. Here is the puzzle. If nothing can travel faster than light, How did regions of space that are now billions of light years apart manage to stay in contact long enough to reach the same temperature and density? We see this uniformity in the cosmic microwave background, the faint glow left over from the Big Bang, remarkably even in all directions. The answer lies in a brief, violent phase called inflation. In a fraction of a second, space itself expanded faster than light could travel through it. Note the crucial distinction. Nothing moved through space faster than light. Space itself stretched, carrying distant regions apart at superluminal speeds. This is allowed because the speed limit applies to motion through space, not to the expansion of space itself. Inflation solved the uniformity problem, but it also pushed potential partners in causality far beyond each other's horizons. Regions that were once in close contact were suddenly separated by distances light could never hope to cross. The universe became divided into vast causal patches, bubbles of reality that can never again influence one another. Our observable universe is one such bubble. Beyond it lies more space, perhaps infinitely more, filled with galaxies and stars and perhaps life, all forever beyond reach, not because of distance alone, but because the speed limit combines with expansion to make communication impossible. The cosmos is not just large. It is fragmented into isolated domains, each evolving independently. This isolation feels profound. If other intelligent beings exist in distant regions, we can never meet them, never exchange knowledge, never even confirm their existence directly. The speed limit, combined with cosmic expansion, enforces solitude on the grandest scale. Yet within our own observable bubble, the same rule creates beauty as well as barriers. Consider the life cycle of stars. Massive ones burn brightly and briefly, exploding as supernovae that scatter heavy elements into space, the carbon in your body, the oxygen in your breath, the iron in your blood. These explosions release neutrinos, ghostly particles that interact so weakly they pass through entire planets unnoticed. Billions stream through you every second. When a star explodes, these neutrinos race outward at speeds indistinguishable from light, arriving minutes before the visible light, because light is slowed slightly by the dense stellar material. Detectors buried deep underground have captured these neutrino heralds from actual supernovae, confirming once again that nothing outruns light, yet things can arrive almost together when traveling near the boundary. The same limit shapes the behavior of particle accelerators. Scientists push protons to speeds where their effective mass is thousands of times greater than at rest. Collisions release showers of new particles, some living only fractions of a second before decaying. Yet even in these extreme conditions, no particle with mass ever crosses the line. The detectors record energies and momenta that match relativity's predictions to extraordinary precision. Every experiment, every observation, every natural phenomenon adds another layer of confirmation. The prohibition is absolute. But why? Why does the universe enforce this particular rule so rigorously? Some physicists suggest it is tied to the nature of causality itself. Allow faster-than-light motion, and the orderly sequence of cause and effect breaks down. Imagine a particle that could zigzag back and forth across the light barrier. In some frames of reference, its path would loop backward in time. Effects could precede causes. Paradoxes would proliferate. The universe appears to have chosen consistency, a single, unambiguous timeline over unrestricted connectivity. Others speculate deeper connections. The speed of light appears in many fundamental constants, linking electricity and magnetism, governing the strength of forces, setting the scale of atomic sizes. Change it and chemistry unravels. Stars might not form. Life as we know it becomes impossible. The limit may be necessary for the kind of stable, complex universe that can host observers like us. Still others wonder whether the prohibition is truly absolute everywhere. Quantum mechanics introduces strangeness, particles entangled across distances, appearing to influence one another instantly. Yet even here, the rule holds. No usable information travels faster than light. The correlations are real, but random. You cannot send a message through entanglement without a classical channel limited by light speed. Nature teases us with apparent loopholes, then closes them firmly. As we accumulate these threads, black holes hiding their secrets, inflation isolating cosmic regions, accelerators confirming the energy barrier, neutrinos racing from dying stars, the picture sharpens. The speed of light is not an inconvenience to be overcome. It is a foundational feature, as essential as gravity or time itself. It protects the coherence of reality. It enables the vastness we observe. It enforces the solitude that may be the natural state of intelligent life, and it humbles us, reminding us that some boundaries are not meant to be crossed. The evidence continues to mount, drawing us toward ever larger implications. In the parts ahead, we will explore how this limit influences the ultimate fate of the universe, how it shapes the possibility of advanced civilizations, and how it forces us to reconsider what exploration truly means when physical travel becomes forever limited. The journey deepens. The cosmos grows both more majestic and more lonely with every step. The deeper we travel into this story, the more the speed limit reveals itself not as a mere rule, but as the quiet architect of everything we see. It draws boundaries around black holes, isolates vast regions born in the same cosmic fire, and guards the arrow of time with absolute vigilance. Yet its influence reaches even farther, into the ultimate fate of the universe itself, into the possibility of advanced life, and into the very meaning of exploration when physical reach is forever curtailed. Let us begin with the end. Picture the cosmos not as it is today, a vibrant tapestry of galaxies swirling in the darkness, but as it may become in the distant future. Stars burn out one by one. New ones fail to ignite as the raw material for starbirth grows scarce. Galaxies dim, their spiral arms unraveling into loose halos of ancient red dwarfs and wandering corpses of dead suns. Black holes, patient and insatiable, slowly consume whatever drifts too close. Over unimaginable stretches of time, even protons, the sturdy building blocks of ordinary matter, may begin to decay if certain theories prove true. Atoms unravel. Electrons and positrons spiral into oblivion, releasing faint whispers of light. What remains is a cold, diffuse sea of radiation and evaporating black holes, each one shrinking gradually as it leaks energy through a subtle quantum process predicted decades ago. When the last black hole finally fades, the universe settles into perfect darkness and perfect stillness, a state of maximum disorder where nothing ever happens again. This vision, bleak yet strangely serene, is called the heat death. It emerges directly from the laws of thermodynamics, but the speed of light plays a crucial role in making it inevitable. Because nothing can travel faster than light, the universe's expansion, driven by a mysterious energy-permeating empty space, carries galaxies away from one another at speeds that increase with distance. Close neighbors drift apart gently. Distant ones recede faster than light itself can bridge the gap. Space expands, not objects moving through it. The speed limit remains unbroken, yet the separation grows without bound. Over time, more and more of the universe slips beyond our causal horizon, the boundary beyond which light emitted today will never reach us, no matter how long we wait. One by one, galaxies blink out of sight, their light stretched into invisible wavelengths, their existence reduced to memory and mathematics. Our local group of galaxies, the Milky Way, Andromeda, and a handful of smaller companions, will merge into a single island universe, surrounded by endless void. Everything beyond that island becomes forever inaccessible, not just in practice, but in principle. The speed limit, combined with accelerating expansion, sentences the cosmos to fragmentation followed by isolation followed by dissolution. This is not speculation born of pessimism. Observations of distant exploding stars, measurements of the cosmic microwave background, and the distribution of galaxies all point to the same conclusion. The expansion is speeding up, driven by an energy whose nature remains elusive. The universe is not only expanding, it is running away from itself. And because no signal can outrun light, there is no way for distant regions to stay connected once the gulf widens beyond the horizon. This cosmic dispersal feels like the ultimate expression of the prohibition we began with. The same rule that keeps ships from reaching nearby stars in human lifetimes now ensures that even light itself cannot hold the universe together forever. Yet there is a strange beauty in this fate. The heat death is the most peaceful end imaginable, no catastrophic crunch, no fiery big rip, just a gentle fading into equilibrium. But it raises a haunting question. If the universe is destined for eternal silence, what does that mean for any intelligence that arises within it? Consider a civilization far more advanced than ours. They master fusion, harness the full output of their star, perhaps even rearrange solar systems. They send probes to nearby worlds, establish outposts in their stellar neighborhood, but the speed limit remains. Even their most ambitious vessels crawl across interstellar distances on timescales of generations. Colonies become independent almost immediately, separated by centuries of communication lag. As expansion accelerates, even those nearby outposts drift beyond practical reach. Messages grow fainter, delayed by ever-lengthening intervals. An advanced species might attempt grand engineering, moving entire stars to cluster them against the coming cold, or constructing artificial worlds powered by black hole energy. Some speculate about harvesting the slow leakage from evaporating black holes, extracting usable power from the quantum glow at their horizons. Yet even these feats buy only time. The heat death waits patiently, indifferent to ingenuity. The speed limit ensures that no civilization, no matter how clever, can gather the resources of an entire galaxy, let alone the universe. Energy sources remain scattered across distances that grow faster than any fleet could traverse. The galaxy becomes a vast archipelago of isolated pockets, each civilization, if any exist, confined to its local cluster, unaware of others, unable to combine knowledge or effort on cosmic scales. This isolation may explain something profound about our own place in the story. We look out at a galaxy teeming with stars, many circled by planets in habitable zones. Simple chemistry seems inevitable wherever liquid water and carbon exist. Yet we have found no unmistakable signs of intelligence elsewhere, no radio signals, no megastructures dimming stars, no evidence of engineering on planetary scales. Perhaps intelligence is rare because life is hard to start. Or perhaps it starts easily, but the speed limit makes the galaxy effectively empty for practical purposes. Any civilization is trapped in its own light cone, the region of space from which signals can reach it within the age of the universe. Even if neighbors exist a few hundred light years away, communication takes centuries. Coordination is impossible. Shared projects across the galaxy become fantasies. Advanced societies may choose silence, conserving energy for the long dark ahead. Or they may simply never overlap in time, one rising as another fades. The speed limit does not just limit travel, it limits connection. This realization shifts our perspective on exploration. We have long dreamed of sailing to other worlds the way ancient mariners crossed oceans. But oceans have currents, winds, no absolute barriers. Space is different. It is not a medium to conquer, but a structure that resists conquest at the deepest level. True exploration, then, may lie not in physical journey, but in observation and understanding. Our telescopes already reach across billions of light years, capturing light that left its source before Earth existed. We see galaxies in their youth, stars being born in vast nurseries, planets forming from swirling disks. Each photon that reaches us has traveled unimpeded at the universal speed, carrying information from places we can never touch. In a sense, light is the only traveler permitted to cross the cosmos freely, and by catching it, we participate in the journey. Future instruments, vast arrays floating in space, sensitive to gravitational waves, neutrinos, and every whisper of radiation, will extend this reach further. We may map exoplanets in detail, read their atmospheres, detect signatures of biology or technology. We may witness events near the universe's birth or watch black holes merge in distant clusters. But we will do so as observers, not visitors. This shift feels like a maturation. Childhood dreams of conquest give way to adult appreciation of distance and mystery. The universe offers itself to our gaze, but withholds itself from our grasp. And perhaps that is mercy as much as prohibition. Because if faster-than-light travel were possible, the consequences might be catastrophic. Causality violations could unravel reality itself. Paradoxes could propagate, destabilizing the coherent timeline that allows complex structures, planets, life, minds to exist. An unrestricted universe might be chaotic, short-lived, incapable of hosting observers. The speed limit may be the price of stability. It ensures that the past remains fixed, that causes reliably produce effects, that history has direction. Without it, the orderly evolution from Big Bang to stars to planets to life might never occur. The prohibition that isolates us may also be the guardian that permits us to exist at all. As we gather these threads, the fading of galaxies beyond horizons, the inevitable drift toward heat death, the enforced solitude of civilizations, the shift from travel to observation, the picture becomes both grander and more intimate. The speed of light is not an obstacle placed in our path. It is the foundation upon which the path is built. It defines the scale of the possible. It protects the coherence of time. It sculpts the destiny of everything. And in doing so, it invites us to find meaning not in reaching, but in seeing, not in possessing the stars, but in understanding our place among them. The evidence continues to accumulate, each layer revealing new depths. Ahead lie questions about the quantum world, where rules bend in subtle ways, about the nature of dark energy driving expansion, about whether any loophole, however exotic, could ever soften the boundary. The journey stretches onward, carrying us toward implications that touch the core of existence itself. The universe has revealed itself layer by layer as a place of exquisite order held together by unbreakable restrictions. The speed of light stands as the central pillar, the rule that prevents chaos in time, enforces isolation across vast distances, and guides the cosmos toward its quiet, inevitable end. Yet even as this picture solidifies, new questions arise at the edges where relativity meets the quantum world, the domain of the extremely small, where particles dance in ways that seem to mock every classical intuition. Imagine zooming inward from the grand scale of galaxies and black holes until you reach the realm of atoms and even smaller. Here, reality behaves less like solid objects and more like waves of probability. Particles can exist in multiple states at once, can tunnel through barriers that should block them, can become linked across distances in ways that feel instantaneous. This is the quantum world, and for nearly a century, physicists have wrestled with how to reconcile it with the smooth, predictable curves of relativity. The tension feels profound. Relativity paints a picture of spacetime as a continuous fabric, bending under mass and energy. Quantum theory describes fields that fluctuate wildly at tiny scales, giving birth to particles from empty space itself. When these two great theories meet, especially in extreme conditions like the hearts of black holes or the first moments of the Big Bang, they clash. The equations break down, producing infinities where sensible answers should appear. Yet even in this apparent conflict, the speed limit holds firm. One of the most tantalizing quantum phenomena is entanglement. Picture two particles created together in a single event. They fly apart in opposite directions, perhaps across the entire laboratory, perhaps across the solar system. Measure a property of one, say, its spin direction, and the other particle instantly shows the correlated result, no matter how far away. The correlation appears immediate, as if information passed between them faster than light. Early physicists worried this might violate the prohibition. Einstein himself called it spooky action at a distance, uncomfortable with the implication that something could influence something else without delay. But deeper analysis revealed a subtle truth. Entanglement does not allow usable information to travel faster than light. The correlations are real but random. When you measure one particle, you cannot control the outcome. It is probabilistic. The distant particle matches perfectly, but you cannot use this to send a deliberate message. To communicate, you still need a classical channel, a radio signal, a letter, something limited by light speed, to compare results and extract meaning. Nature offers a glimpse of connection without granting the power to exploit it. Experiments have pushed this boundary to extraordinary limits. Entangled photons have been sent across cities, through optical fibers, even between ground stations and satellites orbiting overhead. The correlations remain perfect, yet no signal outruns light. The prohibition stands unbroken. This resilience appears again in attempts to probe the very structure of spacetime at the smallest scales. Some theories suggest that space itself is not smooth, but granular, made of tiny, indivisible units far smaller than any particle we can detect. If true, this quantum foam might blur the sharp edges of relativity. Yet every search for deviations from relativity's predictions has come up empty. Light from distant cosmic explosions, gamma ray bursts, arrives with high-energy and low-energy photons side by side, having traveled billions of years across expanding space. If spacetime were foamy enough to scatter higher-energy light more than lower-energy light, the sharp bursts would arrive smeared out over time. They do not. The pulses remain crisp, placing extraordinarily tight limits on any graininess. Clocks based on atomic transitions, flown on aircraft or beamed into space, match relativity's predictions to parts in a trillion. Particle collisions and accelerators produce showers of debris whose energies and angles fit the relativistic framework perfectly, even when probing distances smaller than the nucleus of an atom. The speed limit survives every assault from the quantum realm, but the clash between the two theories points towards something deeper, a need for unification. Physicists have long sought a quantum theory of gravity that would blend the rules seamlessly. String theory, loop quantum gravity, and other candidates offer glimpses of possible resolutions. In some of these pictures, the speed of light emerges as a collective property, like the speed of sound in air arising from the motion of countless molecules. change the underlying structure, and the effective limit might shift. Yet in our universe, the constants appear fixed with exquisite precision. Alter the speed of light even slightly, and the balance of forces shifts. Atoms become unstable. Stars burn too quickly or not at all. Chemistry unravels. The prohibition seems tuned to allow the long, slow evolution that led to complexity, planets cooling over billions of years, life emerging through gradual selection, minds arising capable of pondering their own existence. This fine-tuning feels uncanny. Why these particular values? Why this particular limit? Some speculate multiple universes, a vast ensemble where constants vary, and we find ourselves in one that permits observers, because only such universes can host questioning beings. Others see it as evidence of design, though science remains silent on ultimate purpose. Whatever the reason, the speed limit appears essential to the kind of cosmos we inhabit. This essential nature reveals itself dramatically near black holes, where quantum effects meet extreme gravity. Imagine approaching the horizon we discussed earlier. From far away, it appears frozen, time stretched to infinity. But quantum theory predicts that empty space near the horizon is not truly empty. Particle-antiparticle pairs constantly flicker into existence, borrowing energy from the vacuum for brief moments before annihilating. Near the horizon, the intense tidal forces can separate these pairs. One falls inward, the other escapes outward as real radiation. The black hole slowly leaks energy, Hawking radiation, named after the physicist who first predicted it. Over immense timescales, even massive black holes evaporate completely, returning their energy to the universe as a faint glow. This process resolves one of the great paradoxes. Black holes seem to destroy information, violating quantum rules that demand information be preserved. The radiation carries away the information in subtle correlations, encoded in ways we barely understand. Yet again, nothing escapes the interior faster than light. The horizon remains absolute. The evaporation is slow, patient, limited by the same boundary that traps everything else. Even in the quantum glow, the prohibition holds. These frontier ideas, entanglement without communication, fine-tuning of constants, quantum evaporation of horizons, add new shades to our picture. The speed of light is not a crude barrier slapped onto an otherwise free universe. It is deeply intertwined with the quantum fabric, with the stability of matter, with the possibility of complexity enduring long enough to reflect on itself. Violate it and the delicate balance collapses. Preserve it and you get vast emptiness punctuated by rare islands of structure, stars, planets, life, separated by gulfs that ensure independence. This independence may be crucial. Imagine a universe without the limit. Civilizations could spread instantly, signals crossing galaxies in moments. Knowledge would flow freely. Conflicts could escalate without delay, but so could errors. A single misguided action could propagate catastrophically. Causality loops might destabilize entire regions. The prohibition forces patience. Growth happens locally, slowly. Mistakes remain contained. Evolution proceeds through trial and error on isolated stages. Life learns caution because consequences arrive predictably after causes. The arrow of time remains sharp because effects cannot loop back to erase their origins. In this light, the speed limit feels less like punishment and more like protection. It grants the universe the stability needed for delicate structures to emerge and persist. It allows stories to unfold with beginning, middle, and end. It gives meaning to distance and to striving. As we gather these insights, from quantum entanglement that teases but never delivers superluminal messages, from the fine-tuning that makes chemistry possible, from the slow quantum death of black holes that preserves information without breaking the horizon, the prohibition grows ever more central. It is not an accident or an inconvenience. It is the quiet rule that makes everything else possible. Yet questions remain. Modern experiments push the boundaries further. Vast networks of detectors search for gravitational waves from the early universe, ripples that traveled freely at light speed across the inflating cosmos. Neutrino observatories buried in ice or deep lakes capture ghostly particles from supernovae and cosmic rays, confirming once more that they arrive just behind or alongside light, never ahead. Future colliders may probe energies where quantum gravity effects become detectable, perhaps revealing the underlying structure that enforces them. Space-based interferometers will measure space-time distortions with precision that could uncover tiny deviations, or confirm the theory yet again. Each advance adds weight to the same conclusion. The prohibition is woven too deeply to be accidental. The universe has chosen, or has been shaped to choose, order over anarchy, separation over instant unity, patience over haste. And in that choice lies both the grandeur and the melancholy of existence. We stand on a small world, gazing at stars we can study but never visit, understanding laws we can describe but never overturn. Our reach is limited, but our vision extends to the edge of the observable cosmos. Light brings us the universe, one photon at a time, and perhaps that is enough. The journey continues, carrying us toward the deepest implications yet, how this limit shapes consciousness itself, how it defines the human condition in a cosmos both intimate and infinite. The evidence builds, the wonder deepens. We have traveled far in this exploration, from the quiet failure of an experiment in a forgotten basement to the slow evaporation of black holes in the distant future, from the enforced solitude of civilizations to the subtle protections woven into the quantum fabric. Every path leads back to the same unyielding boundary. The speed of light stands as guardian, architect, and judge, shaping reality in ways both beautiful and unforgiving. Yet the story does not end with acceptance. It presses onward into territory where the prohibition feels not just physical, but almost personal, where it touches the nature of consciousness, the meaning of ambition, and the quiet longing that drives every human gaze toward the night sky. Imagine yourself alone on a hillside under a clear desert sky. The air is cold and still. Above you, the Milky Way arches like a river of frost. Each point of light is a sun, many with worlds circling them, some perhaps bearing oceans, forests, cities, minds looking back at a sky that contains your own distant star. You feel the pull, the ancient urge to reach out, to cross the void, to know that you are not alone in the darkness. This longing is not childish fantasy. It is woven into our biology, our myths, our art. Every story of flight, every tale of exploration, every dream of wings or sails or engines reflects the same deep impulse, to overcome separation. And yet the universe answers with silence, not cruelty but law. The prohibition is absolute, yet it invites a different kind of reaching, one that happens not through motion but through understanding. Because while matter is bound, light is free. Every photon that reaches your eye tonight began its journey long ago. Some left their stars when humanity still lived in caves. Others set out before Earth had oceans. They traveled unimpeded, untouched by friction or resistance, carrying perfect records of their origins. In catching that light, we touch the past directly. We hold evidence from places we can never visit, events we can never witness in person. This is the true mode of cosmic exploration, passive, patient, profound. Consider what we have already achieved with this method. We have watched stars explode across the galaxy, their death throes announcing the forging of heavy elements that later coalesced into planets like ours. We have seen disks of gas and dust swirling around young suns, catching the first glimmers of planet formation, worlds being born in real time, though the light we see is ancient. We have peered into the nurseries where massive stars cluster, their fierce radiation carving bubbles in vast clouds, triggering new generations of birth. We have detected worlds circling distant stars not by seeing them directly, but by the subtle shadows they cast or the tiny wobbles they induce in their parent suns. Some of these worlds sit in zones where liquid water could persist. Some show atmospheres rich in gases that on Earth are produced by life. We have even begun to read the chemical fingerprints of those atmospheres, searching for imbalances that might betray biological activity. All of this without leaving our solar system. Light brings the universe to us, obediently respecting its own speed limit, yet spanning distances that matter never could. And future instruments will extend this reach dramatically. Imagine vast arrays of telescopes working together across continents or floating in space, their mirrors linked to form eyes larger than cities. They will resolve surface features on distant worlds, oceans glinting, continents outlined, perhaps even artificial lights on a night side. Other detectors will catch gravitational waves, ripples in spacetime from merging black holes or neutron stars, signals that travel at the speed of light but carry information light itself cannot, the hidden motions of invisible masses. Neutrino observatories will grow larger, capturing more of those elusive particles that stream from stellar cores, revealing the hidden fusion fires that power suns. Each new window adds depth to the picture, turning points of light into rich, detailed worlds. This form of exploration demands patience spanning generations. A telescope launched today may return its richest data long after its builders are gone, yet it binds humanity together across time. Knowledge accumulates, passed forward like a relay torch. The prohibition that bars physical travel forces us toward this collective, long-term endeavor, one that rewards cooperation, careful observation, and humility before the vastness. It transforms ambition from conquest to contemplation. And in that transformation lies unexpected freedom, because while a ship is bound by fuel and time dilation, understanding is not. An idea can leap from mind to mind instantly, across a room or across centuries through recorded thought. The laws we uncover apply everywhere. The patterns we discern in our local corner reflect universal truths. By studying the light that reaches us, we reconstruct events billions of years past and billions of light years away with astonishing precision. We trace the evolution of galaxies, watch them collide and merge, see supermassive black holes grow at their centers. We map the large-scale structure of the cosmos, vast filaments of galaxies surrounding enormous voids, a cosmic web stretched across the observable universe. All of this emerges from photons that obeyed the speed limit faithfully, arriving exactly when they should, carrying undistorted messages from the depths of time. This fidelity is itself a gift. Because the speed is constant, we can trust the information. Redshifts tell us reliably how fast things recede. Brightness reveals true power. Polarization uncovers magnetic fields threading space. The prohibition ensures the universe remains legible. Without it, light might slow or speed depending on source or medium, scrambling the signals, turning the sky into noise. Instead, we receive clear postcards from everywhere and everyone within our horizon. This legibility invites a profound shift in perspective. We are not prisoners staring at walls. We are inhabitants of a vast library, where every direction offers shelves stretching to infinity, filled with volumes written in light. Our task is not to escape the library, but to read as deeply as possible, and reading changes us. Understanding the speed limit does not diminish wonder, it deepens it. Knowing that the stars are forever beyond reach makes each photon more precious. Knowing that we are bound to this small world makes our capacity to comprehend the whole more miraculous. The prohibition highlights the asymmetry at the heart of existence. Matter is local, information is cosmic. We are made of stuff that cannot escape its light cone, yet we host minds that can reconstruct events far outside it. This duality feels almost poetic. The same rule that isolates bodies connects minds through shared discovery. Every culture that has ever looked upward has told stories about the sky. Now we tell a truer story, one confirmed by evidence from every corner of the observable cosmos. And that story is still unfolding. New observatories rise on high mountains and in cold deserts, chosen for clear air and dark skies. Space telescopes orbit above the atmosphere, free from its blur and glow. Gravitational wave detectors stretch arms kilometers long, sensing distortions smaller than atomic nuclei. Neutrino traps fill vast caverns with pure water or ice, waiting for rare flashes from passing ghosts. Each instrument adds voices to the chorus. Together, they reveal a universe more complex than earlier generations dared imagine: dark matter shaping galaxies, dark energy driving acceleration, quantum fluctuations frozen into the microwave background from the inflationary era. All consistent with the same foundational rules, the speed limit chief among them. This convergence feels reassuring. Reality hangs together coherently, no loose threads, no arbitrary exceptions. The prohibition is not a flaw to be fixed. It is a feature that makes the rest possible, yet the human spirit resists final acceptance. We continue to dream of shortcuts, wormholes threading space, Alcubierre drives contracting spacetime ahead while expanding it behind. These ideas live in the mathematics, elegant solutions to Einstein's equations that seem to permit faster-than-light effective travel without local violation of the speed limit. Matter and light still move normally within the bubble, but the bubble itself surfs on warped space. The catch is severe. Such configurations require exotic matter with negative energy density, something we have never observed in bulk, and that may violate fundamental energy conditions. Even if possible, many physicists argue they would be unstable or allow causality violations through closed time-like curves. Nature seems to close every door firmly. Quantum gravity may ultimately forbid them, preserving the prohibition at a deeper level. We search for signs of advanced civilizations that might have overcome the limit: megastructures harvesting entire stars, artificial black holes powering computation, probes self-replicating across the galaxy. So far, silence. This absence may simply confirm the barrier's strength. No technology, however advanced, can rewrite the laws. or it may suggest we are early or alone, or that intelligence naturally turns inward rather than outward when confronted with the true scale. Whatever the reason, the search itself refines our understanding. Every negative result tightens the constraints. Every new observation confirms the framework. The prohibition stands, serene and absolute, and in standing, it offers clarity. We know the shape of the possible. We know where to direct our wonder. We know that the universe, vast and ancient, has arranged itself in such a way that fragile temporary beings on a small world can nevertheless decipher its deepest patterns. This knowledge is not consolation prize. It is triumph. The speed limit does not diminish us. It elevates the act of understanding to cosmic significance. Because in a universe where matter is bound, the unbound mind becomes the rarest and most precious phenomenon. Light brings the cosmos to us. We receive it with gratitude, decode it with care, and pass the understanding forward. The longing to reach the stars remains, transformed into the quieter, deeper longing to know them. And in that knowing, we touch them after all. The journey presses on. Ahead lie the ultimate questions: what this prohibition implies for the existence of observers, for the nature of reality itself, for the possibility that the universe is not indifferent but finely crafted for discovery. The evidence accumulates, the perspective widens, the awe intensifies. The prohibition has revealed itself not as a distant law written in some cosmic code, but as something intimate, a boundary that shapes every moment of awareness, every reach of curiosity, every quiet moment when a human being looks up and feels the weight of the sky. Light is permitted to roam freely, carrying the universe to us in perfect fidelity. Matter, and with it, the fragile assemblies we call bodies and minds, remains forever local, confined to narrow cones of causality. This asymmetry lies at the heart of the human condition. We are creatures born from stardust, assembled through billions of years of slow chemistry on a single small world, yet capable of reconstructing the history of everything. We can trace the expansion back almost to the beginning, calculate the masses of invisible black holes, predict the slow fade of protons in a future so remote it defies comprehension. And we can do all this while standing firmly planted on the ground, never leaving the surface that birthed us. The speed limit makes this miracle possible. Without it, the universe might be a chaotic blur, light arriving at different speeds from different sources, distances impossible to gauge reliably, time scrambled across regions. The coherent narrative we have pieced together would dissolve into noise. Instead, we receive a consistent, legible cosmos. Every observation fits the same framework. Every new discovery reinforces the old ones. This consistency invites trust. We do not merely guess at the laws, we confirm them again and again with ever greater precision. And in that confirmation lies a profound reversal. The rule that seems to confine us is the very thing that liberates our understanding. Imagine a universe without the limit. Matter and information could leap instantly across any distance. Horizons would vanish. Isolation would end, but so would stability. Causality loops could form spontaneously. An effect could erase its own cause. Entire regions might blink in and out of existence as paradoxes resolve themselves destructively. Complex structures, galaxies, stars, planets, life, require long stretches of unbroken time to form and endure. They need reliable sequences where chemistry builds step by step, where evolution proceeds through gradual selection. A universe permissive of superluminal motion might never hold still long enough for such delicacy to emerge. The prohibition, then, may be the prerequisite for observers. It ensures that the cosmos evolves slowly enough, coherently enough, for pockets of low entropy, like our solar system, to persist and give rise to complexity. This idea echoes through modern cosmology in subtle ways. Consider the flatness of the universe. Observations show spacetime is almost perfectly flat on large scales, neither curving closed like a sphere nor opening endlessly like a saddle. If it were even slightly more curved in either direction, the universe would have either collapsed back on itself early on or expanded so rapidly that galaxies never formed. The measured flatness is exquisite, to within a tiny fraction. Inflation explains this by stretching a small, causally connected patch to enormous size, smoothing out any initial curvature. But inflation itself relied on the speed limit remaining intact. The rapid expansion stretched space, not matter, through space. The prohibition allowed the smoothing without violating local rules. Similar fine-tuning appears in the balance between matter and dark energy. Too much matter and gravity wins early, collapsing everything before life can arise. Too much dark energy and expansion accelerates too soon, preventing galaxies from condensing. We find ourselves in the narrow window where structure forms, stars live long enough to forge heavy elements, and the cosmos remains connected long enough for light from distant regions to reach us before acceleration pulls them away forever. The speed limit plays its part here too, setting the scale at which gravity and expansion compete. Change it significantly and the timing shifts. Stars burn differently. Chemistry alters. The window for observers narrows or vanishes. This recurring theme of fine-tuning raises questions that science approaches cautiously but cannot ignore. Why these particular values? Why this particular limit? One response is anthropic. In a multiverse ensemble where constants vary, we necessarily find ourselves in a universe that permits our existence. Universes without observers go unnoticed. Another view sees the tuning as evidence of selection, perhaps through eternal inflation spawning bubble universes with different laws, and only some bubbling up complexity. Still others leave the question open, acknowledging that science describes how, not ultimately why. Yet the prohibition remains central in every scenario. It is not one constant among many. It ties together electricity and magnetism, sets the strength of electromagnetic interactions, governs the size of atoms and the stability of orbits. It appears in the very equations that describe fields and particles. Change it and the cascade is dramatic. Stars might collapse directly to black holes without fusing elements, or they might burn too feebly to warm planets. Chemistry might lack the rich diversity needed for life. The speed limit is not arbitrary, it is deeply embedded. This embedding suggests the prohibition is not a late addition, but a foundational feature. In some quantum gravity candidates, it emerges from more basic principles, the way discrete structures give rise to an effective continuum speed. In others, it reflects the invariance of spacetime intervals, the unchanging measure that separates time-like from space-like paths. Every path leads back to the same conclusion. The universe is constructed in such a way that causality is preserved at all costs. And in preserving causality, it creates the conditions for narrative, for stories with direction, for histories that accumulate rather than loop or fracture. Consciousness itself may depend on this directionality. We experience time as flowing forward because entropy increases, because causes precede effects, because the universe remembers its past in the arrangement of matter and radiation. Memory requires reliable records. Prediction requires consistent laws. Both rest on the arrow enforced by the speed limit. Imagine a mind in a universe where effects could precede causes. Planning would be meaningless, learning from experience impossible. Identity itself might dissolve as past and future blurred. The prohibition gifts us the stable platform on which self-awareness can stand. It allows the slow accumulation of knowledge across generations. It makes science possible. Each telescope we build, each detector we bury, each probe we launch extends our light cone slightly, gathering more of the allowed information. We cannot expand our physical reach, but we can expand our causal reach through patient observation. This expansion feels like growth in a different dimension, where bodies are bound, understanding stretches. And in that stretching lies purpose. Humanity's story becomes not one of conquest across space, but of deepening comprehension within the allowed sphere. We map the observable universe in ever finer detail, tracing filaments of dark matter, charting the mergers of ancient galaxies, reading the echoes of primordial sound waves in the microwave sky. Each advance reveals new layers, exoplanets with potential biosignatures, gravitational waves from events too violent for light to fully describe, neutrinos carrying messages from stellar cores. The prohibition does not diminish these discoveries, it frames them. Because we know the light has traveled far, obeyed the limit faithfully, we value the information more deeply. Because we know we cannot go there ourselves, the act of seeing becomes sacred. This perspective transforms isolation into privilege. We are not abandoned in the void. We are positioned at a vantage point where the entire visible history of the cosmos converges on a single small world at a single moment in time. Billions of years of evolution across billions of light years, all funneling down to sensors on a pale blue dot. The convergence feels almost orchestrated, as if the universe arranged itself so that, at least once, a fragment of it could become aware of the whole. The speed limit ensures this awareness remains contemplative rather than consumptive. We cannot exploit distant resources. We cannot interfere with faraway worlds. We can only watch, learn, and wonder. This restraint may be wisdom built into reality itself, because any species that overcame the limit might also overcome caution. Instant travel could enable instant conflict. Paradoxes could threaten stability. By enforcing separation, the prohibition allows diversity to flourish undisturbed. Different regions evolve independently. Different forms of complexity arise in isolation. If life is common, it may take countless unique paths, unhindered by contact. The galaxy becomes a vast experiment in possibility, each star system a separate trial. Our role is not to unify it, but to witness one thread. And perhaps, through understanding the prohibition, we gain insight into why the experiment is structured this way. The evidence continues to speak with one voice. From the precise orbits of binary pulsars losing energy exactly as relativity predicts through gravitational radiation, to the frame-dragging effects measured around spinning black holes, to the absence of any confirmed superluminal signal in decades of searching, every test reaffirms the boundary. Future experiments will push harder. Next-generation gravitational wave observatories in space will detect ripples from the earliest moments after the Big Bang, when quantum gravity effects might have left faint signatures. Vast neutrino detectors will capture streams from across the galaxy, testing whether these nearly massless particles ever nudge past the limit. Precision tests in laboratories will search for tiny violations in particle decays or atomic transitions. So far, nothing. The prohibition holds as firmly as ever. And in holding, it continues to shape our destiny. We build ever better instruments not to break the rule, but to work within it more elegantly. We send probes to nearby worlds, Mars, Europa, Titan, exploring our local neighborhood while accepting the larger gulf. We develop simulations that reconstruct distant events with increasing fidelity, bringing the universe into virtual reach. We cultivate wisdom that values understanding over possession. The longing persists transformed. It becomes the drive to see farther, to know deeper, to pass the torch brighter to those who follow. Because while our bodies remain bound, the light we catch and the knowledge we build can travel forward in time, carried by minds yet unborn. In this way, we escape the limit after all, not through speed, but through legacy. The prohibition that confines us in space liberates us in time. Our story does not end with resignation. It continues with resolve to make the most of the vision granted us, to read the light with care, to honor the vastness by seeking to comprehend it, to find meaning in the act of seeing clearly. The journey deepens further. Ahead lie the final syntheses, how the prohibition resolves the greatest paradoxes, how it points toward ultimate unity beneath apparent separation, how it invites us to a maturity that embraces limits as the source of depth. The cosmos speaks. We listen. The prohibition has become more than a physical law. It has revealed itself as the silent condition for everything we cherish. The arrow of time that gives stories direction, the stability that allows complexity to endure, the isolation that protects diversity while granting us the unique privilege of comprehensive vision. We receive the universe not by grasping it, but by allowing its light to reach us, patient, faithful, bound by the same rule that binds us. Yet this acceptance does not quiet the mind. It sharpens the questions. If the speed limit is so deeply protective, so finely woven into the possibility of observers, then what does it imply about the larger reality we inhabit? Is the universe indifferent, merely happening to have the right constants for life and mind? Or does the exquisite balance suggest something more deliberate, a cosmos structured for discovery? These are dangerous waters for science. They border on philosophy, even theology. Yet the evidence itself pushes us toward them. Consider again the narrow window in which we exist. The universe is old enough for stars to have lived and died multiple times, scattering heavy elements into space. It is young enough that many stars still burn steadily, warming worlds where liquid water can persist. Expansion has proceeded at a pace that allowed galaxies to form and cluster, yet now accelerates just as intelligence emerges capable of noticing the acceleration. Dark energy, the mysterious push driving that acceleration, is tuned to a value so tiny compared to theoretical expectations that physicists call it the worst prediction in their history. Yet if it were much stronger, galaxies would never have condensed. If weaker, gravity might have already pulled everything back into a crunch. The speed limit sits at the center of this balance, linking the strength of forces, the scale of atoms, the lifetime of stars. Change it by a meaningful fraction, and the entire chain unravels. This convergence of constants feels less like coincidence and more like coordination. Some physicists respond by invoking vast ensembles, countless universes with varying laws, ours selected because it permits questioners. The idea is elegant. We observe these particular values because only they allow observation. yet it shifts the mystery rather than resolving it. Why does the ensemble exist? Why variation at all? Others explore whether the constants are truly independent or linked by deeper theory. A complete quantum gravity might reveal why the speed limit takes its specific value, emerging inevitably from more fundamental principles. String theory landscapes suggest enormous numbers of possible vacuum states, each with different effective constants. Again, anthropic selection among them. Loop quantum gravity offers discrete spacetime that might fix certain ratios. None of these frameworks has yet delivered a definitive prediction we can test, but they all preserve the prohibition as central. Even in speculative pictures where extra dimensions curl up tightly, the effective speed in our familiar dimensions remains absolute. The boundary holds. This persistence across theoretical attempts suggests the prohibition is robust, not a fragile accident, but a feature likely to survive future revolutions in understanding. And that robustness invites reflection on purpose, not in the narrow sense of design for a specific species, but in the broader sense of a reality primed for self-awareness. A universe that evolves minds capable of reconstructing its own history, discerning its laws, contemplating its fate. The speed limit plays multiple roles in this priming. It enforces the vast scales that make heavy elements rare and precious, forcing slow stellar evolution. It creates horizons, event horizons around black holes, particle horizons from expansion, that hide certain truths forever, preserving mystery. It ensures that observation outpaces intervention, turning potential explorers into inevitable contemplators. We become witnesses rather than conquerors. This role feels profound. A cosmos without the limit might produce intelligence quickly overwhelmed by its own power, spreading, interfering, destabilizing. With the limit, intelligence arises in isolation, learns humility early, directs energy toward understanding rather than domination. The prohibition schools us in restraint. It teaches that some distances are sacred. That reaching is not always the highest form of connection. That seeing clearly from where we stand can be more intimate than touching. Modern science embodies this lesson daily. We do not send fleets to distant galaxies. We send light collectors, mirrors, and antennas tuned to capture whispers from the edge. The James Webb Space Telescope, floating far from Earth, peers into the deepest past, watching the first galaxies ignite after the Big Bang. Its images arrive as infrared glows, stretched by expansion, yet sharp enough to reveal swirling disks, merging pairs, bursts of star formation in eras when the universe was a fraction of its current age. Each discovery confirms the framework. Redshifts match predictions, brightness distances align with expansion history, structures trace the seeds planted in inflation. No violations. The speed limit obeyed across billions of years. Future instruments will push further. Giant ground-based telescopes with mirrors segmented like insect eyes will gather light from worlds orbiting distant suns, splitting it into spectra that reveal atmospheric composition. We may detect oxygen and methane in ratios that suggest biology, or industrial pollutants that betray technology. Yet even if we find unmistakable signs of life, the prohibition ensures we remain correspondents, not visitors. Messages sent today would arrive centuries or millennia later. Replies would take equally long. Conversation across stars becomes a relay across generations. This timescale forces depth over haste. Any exchange would demand patience, clarity, permanence. We would choose words or mathematics or music meant to endure. The prohibition elevates communication to art. It prevents trivial contact, ensuring that if connection ever occurs, it is meaningful. Some speculate about probes, self-replicating machines launched toward nearby stars, carrying encoded knowledge. Even these would crawl across interstellar distances over thousands of years, and upon arrival, they could only observe or transmit back slowly. The limit remains. Yet within our local realm, we explore actively. Robots roam Mars, sampling rocks that record ancient water flows. Submarines may soon plunge beneath Europa's icy crust, searching for hidden oceans. Probes sniff Titan's thick atmosphere, mapping lakes of liquid methane. These journeys happen at ordinary speeds, demanding ingenuity in miniaturization, autonomy, radiation hardening. Each success expands our physical presence slightly, while reminding us how small that presence remains. The solar system becomes our garden, vast by human scales, tiny against the galaxy. We tend it with care, knowing it may be the only garden we ever have. This realization shifts priorities. We invest in sustainability here because there is no escape hatch to another star. We study Earth's biosphere deeply because it may be the only one we directly touch. We cultivate cooperation across nations and generations because knowledge is the only resource that travels freely through time. The prohibition focuses us inward and outward simultaneously, inward toward stewardship, outward toward comprehension. It resolves a paradox of existence, how to feel at home in an immense, ancient cosmos without feeling insignificant. By limiting reach, it makes our local world precious. By permitting vision, it makes our understanding immense. We are small in space, vast in awareness. The balance feels right. As instruments grow more sensitive, we probe the prohibition itself more directly. Experiments search for photons from distant gamma-ray bursts arriving with tiny timing differences that would signal a breakdown of constancy at high energies. None found. Atomic clocks compare rates with precision that would reveal any drift in fundamental constants over time. Stable. Particle colliders recreate conditions of the early universe, testing whether relativity holds at the smallest scales. It does. Each null result strengthens the framework. Each confirmation deepens the mystery of why. We stand at a moment when the observable universe is still fully accessible in principle. Light emitted from the farthest galaxies is only now reaching us. In another billion years, acceleration will have carried most galaxies beyond our horizon forever. Their light will never arrive. We live in the brief era when almost everything that ever happened is still visible. This timing feels privileged. As if the universe waited until minds evolved to record the full story before beginning to hide it. The prohibition, through expansion, creates this window and then closes it. It grants a complete view to one generation of observers, perhaps the first, perhaps the only. Our responsibility becomes clear, to capture as much as possible, to interpret faithfully, to preserve for whatever future arises in our isolated island. The act of science becomes almost sacred duty, not conquest. Not exploitation, witnessing, and in witnessing, participating, because every measurement we make, every pattern we discern adds to the universe's self-knowledge. A fragment of reality becomes aware of the whole, and in that awareness, the whole reflects upon itself through us. The speed limit enables this reflection by ensuring separation between observer and observed on large scales. We study without disturbing. We learn without consuming. We grow in understanding without growing in dominion. This path feels mature. Childhood dreams of flight give way to adult appreciation of perspective. The longing transforms into gratitude for the light that reaches us, for the time granted to see, for the minds capable of seeing. The prohibition, once seeming like cosmic cruelty, reveals itself as cosmic wisdom. It protects the universe from its own potential chaos. It protects emerging intelligence from premature power. It protects mystery by preserving distance. And it protects meaning by making every discovery hard-won. The journey approaches its deepest layers. Ahead lie the unresolved tensions, the quantum gravity frontier where the prohibition may find its ultimate origin, the dark energy enigma that accelerates our isolation, the possibility that the limit itself evolves in ways we cannot yet detect. The evidence speaks clearly so far. The wonder only grows. The prohibition has guided us through layers of revelation, each one stripping away illusions of freedom and replacing them with a deeper sense of structure. It protects causality, enables complexity, enforces solitude, and transforms raw ambition into refined contemplation. We have come to see it not as a wall blocking our path, but as the very ground beneath our feet, the foundation that makes a coherent, discoverable universe possible. Yet the story refuses to settle into comfortable resolution. At the edges where observation meets the unknown, new shadows gather. Dark matter, dark energy, the quantum gravity frontier. These are not minor footnotes. They are vast domains where the prohibition operates in ways we only glimpse and where its true origin may finally be revealed. Let us begin with the invisible. Imagine looking at a spiral galaxy edge-on, a thin disk of stars glowing against the blackness, bisected by a dark lane of dust. The stars orbit the center in orderly paths, faster near the core, slower at the edges, just as planets orbit the sun. But something is wrong. The outer stars move too quickly. By every calculation based on visible mass, they should fly away into intergalactic space, unbound by insufficient gravity. They do not. For decades, astronomers puzzled over this. The obvious conclusion: most of the mass is missing from view. It neither emits nor absorbs light. It reveals itself only through gravitational pull. We call it dark matter. This unseen substance outweighs ordinary atoms by a significant margin. It forms vast halos around galaxies, threading the cosmic web in filaments that guide visible structure. Without it, galaxies would never have condensed from the smooth early universe. Gravity would have been too weak to gather gas into stars. Dark matter provided the scaffold, and its behavior ties directly to the speed limit. Particles of ordinary matter interact electromagnetically. They scatter light, collide frequently, lose energy rapidly. This friction slows them, allowing collapse into flat disks like our Milky Way. Dark matter does not. It passes through itself and through ordinary matter almost untouched, influenced mainly by gravity. Its particles move at speeds far below light's boundary, clustering loosely, forming extended halos rather than thin disks. This difference arises because dark matter candidates, whatever they are, lack the charges that enable electromagnetic interactions. They feel only gravity and perhaps the weak force, both far feebler at small scales. The speed limit remains absolute for them as well. No dark matter particle has ever been observed exceeding it. Yet their near invisibility allows them to maintain higher average speeds without radiating energy away. They orbit galaxies in wide, slow paths, providing the extra gravity that keeps everything bound. Observations confirm this picture relentlessly. Gravitational lensing, light from distant quasars bent around invisible masses, maps dark matter distributions with precision. Collisions between galaxy clusters separate the hot gas, visible in X-rays, from the gravitational mass, traced by lensing, showing that dark matter passes through ordinary matter unimpeded. Cosmic microwave background patterns reveal its presence in the early universe, influencing how sound waves propagated through the primordial plasma. Every probe, from underground detectors searching for rare interactions to particle accelerators trying to produce it, comes up empty on direct detection. Yet its gravitational signature is unmistakable. Dark matter obeys the prohibition faithfully, but its detachment from light allows it to shape the visible universe from behind a veil. This hidden influence feels almost poetic. The stuff that forms the backbone of cosmic structure cannot itself be seen. It reveals itself only indirectly, through the motion it permits and the light it bends. The speed limit plays its part by ensuring that electromagnetic interactions, the carriers of visibility, remain strong for ordinary matter while absent for the dark sector. Without this separation, everything might mix uniformly, preventing the clumping needed for galaxies. The prohibition, by governing which forces couple to which particles, helps create the contrast between seen and unseen. And this contrast extends to the greatest mystery of all, the acceleration itself. For most of cosmic history, gravity slowed the expansion. Galaxies drifted apart, but the pull of matter acted as a brake. Then, roughly halfway through the universe's age, the trend reversed. Expansion began to speed up. Distant supernovae appear fainter than expected, as if carried farther by an unexpected push. The cosmic microwave background shows a universe flatter than gravity alone could maintain. Galaxy clusters recede faster over time. The culprit, a smooth, pervasive energy that fills empty space, exerting negative pressure, a repulsion that grows dominant as ordinary matter thins out. We call it dark energy. It now dominates the cosmos, driving galaxies apart ever faster, pushing most of them toward horizons we will never cross. Dark energy behaves like a constant inherent to spacetime itself, the cosmological constant Einstein once introduced and later regretted. Its value is tiny beyond comprehension compared to theoretical expectations from quantum fields, yet precisely tuned to allow galactic structure before taking over. And its effect ties intimately to the speed limit. Because nothing material can outrun light, the causal horizon expands at a finite rate. Regions once in contact drift beyond communication. Dark energy accelerates this drift, turning potential connectivity into permanent isolation. In a universe dominated by matter, expansion would slow and perhaps reverse. In one dominated too early by dark energy, structure would never form. We live in the transition era, galaxies already built, acceleration only now becoming evident. The speed limit ensures that light from those forming galaxies still reaches us before they vanish forever. We witness the full history just as the curtain begins to fall. This timing feels privileged, almost deliberate. Dark energy's repulsion acts uniformly, unlike gravity's attraction. It does not clump or vary significantly. Its influence propagates at the speed of light. Gravitational changes, like all influences, cannot spread faster. Ripples in spacetime from merging black holes travel exactly at the boundary, as detected instruments confirm. Dark energy's effect, being inherent to space, expands with space itself. but local measurements remain bound by the prohibition. The interplay between dark matter's pull and dark energy's push sets the cosmic destiny, currently balanced in a way that permits vast structure yet inevitable dispersal. Change the balance, and either collapse or eternal barrenness ensues. The speed limit anchors this balance by defining how quickly influences spread and horizons grow. These dark components, matter that shapes without shining, energy that repels without source, dominate the universe by far. Ordinary atoms, the stuff of stars and life, comprise only a small fraction. We live in a cosmos mostly invisible, mostly repulsive, governed by rules that hide more than they reveal. Yet the visible minority is enough. Stars ignite, planets form, chemistry unfolds, minds arise. The prohibition allows just enough interaction, just enough visibility, for complexity to emerge in rare pockets. It prevents the dark sectors from overwhelming or mixing too thoroughly with the light. This separation feels crucial. If dark matter interacted strongly with light, it might collapse into stars or scatter radiation, altering stellar evolution. If dark energy varied locally, it might tear apart galaxies or planets. Instead, both remain aloof, influencing from a distance, preserving the stage where ordinary matter can play out its slow drama. Modern experiments hunt these shadows relentlessly. Deep underground laboratories shield detectors from cosmic rays, waiting for faint nuclear recoils from passing dark matter particles. Space telescopes map lensing with ever finer resolution, tracing dark matter filaments. Supernova surveys and baryon acoustic oscillation measurements pin down dark energy's properties. Particle colliders probe high energies for signs of new physics that might explain both. So far, the dark remains dark. But each non-detection tightens the constraints, refining the picture. The prohibition holds in the dark as in the light. No signal, no influence exceeds the boundary. Even hypothetical particles proposed as dark matter candidates, axions, sterile neutrinos, weakly interacting massive particles, are bound by the same rule. Speculative alternatives like modified gravity attempt to explain observations without dark components, but struggle to match all data simultaneously. The standard picture endures. As we approach the quantum gravity frontier, the prohibition faces its sternest test. Here, spacetime itself may lose continuity, becoming a froth of fluctuating geometries at scales far smaller than any particle. In this realm, the smooth fabric of relativity meets the probabilistic storms of quantum fields. Black hole horizons pose sharp paradoxes. Information falling in seems lost forever, violating quantum preservation, yet Hawking radiation suggests subtle escape. The resolution likely lies in a unified theory where gravity emerges from quantum entanglement, spacetime from information flow. Some approaches suggest the speed limit arises naturally, the maximum rate at which information can propagate through entangled degrees of freedom. Others see it as the boundary separating time-like from space-like separations in a deeper discrete structure. In all viable candidates, the prohibition survives. It is not overturned, it is explained. This resilience suggests the limit is more fundamental than relativity itself. Relativity may be an effective description, valid on large scales, while the true underlying reality enforces the boundary at a more basic level. The journey toward quantum gravity continues. Space-based interferometers hunt primordial gravitational waves that might carry imprints of quantum fluctuations during inflation. High-energy cosmic rays probe regimes where quantum gravity effects could appear. Theoretical frameworks evolve, seeking mathematical consistency. Each step forward honors the prohibition rather than challenging it. The dark sectors and the unification frontier draw us toward a synthesis. The universe is mostly hidden, mostly accelerating apart, governed by a rule that permits just enough visibility for minds to reconstruct the whole. The prohibition orchestrates this balance. It keeps influences local enough for structure, global enough for coherence. It hides the majority to spotlight the minority where complexity can thrive. It accelerates isolation just as comprehension peaks. We stand at the moment of maximum revelation, gathering light from across the observable cosmos before much of it fades forever. This convergence feels like culmination, as if the entire history, Big Bang, inflation, galaxy formation, stellar evolution, planetary cooling, biological emergence, conscious reflection, aligned to produce witnesses capable of seeing the full arc. The prohibition makes this witnessing possible by enforcing the scales and separations needed for the story to unfold. It prevents premature unity or collapse. It preserves gradients of density, of temperature, of entropy that drive change. It allows the universe to evolve rather than stagnate in equilibrium. In this light, the speed limit appears not as restriction but as liberation. It liberates spacetime to expand freely. It liberates matter to cluster selectively. It liberates information to flow exactly where and when needed. It liberates minds to perceive pattern without being overwhelmed by totality. The dark and the quantum point toward ultimate unity, a reality where separation is illusion, yet the illusion is necessary for experience. We live within the illusion, grateful for its clarity. The evidence converges. From lensing maps to acceleration curves, from null detection results to theoretical consistencies, all affirm the same framework. The prohibition stands at the center, serene and essential. The journey approaches its grandest implications yet, how the limit resolves the origin of everything, how it defines the boundary between known and unknowable, how it invites us to embrace our place with full awareness. The cosmos unfolds. We behold. We began this journey with a provocation that cut to the bone. What if the universe does not merely make interstellar travel difficult? What if it forbids it outright? What if the speed of light is not a hurdle to overcome with better engines, but an absolute wall woven into the fabric of reality itself, designed or evolved to keep every star, every world, every thinking being forever isolated? We started gently with a failed experiment in a quiet laboratory, a null result that refused to go away. Michelson and Morley expected to measure Earth's motion through a hidden medium. They found nothing. Light speed remained stubbornly the same, no matter the direction, no matter the motion of the observer. That single fact forced a young patent clerk to rethink space and time themselves. Einstein did not add complications. He stripped away the unnecessary. Accept the constancy of light, and everything else falls into place. Time stretches, lengths contract, masses swell toward infinity as the forbidden speed approaches. We watch these effects play out in the real world. Muons rain down from the atmosphere, surviving journeys they should not because their clocks tick slower. Satellites adjust their timepieces daily to keep our navigation accurate. Particle accelerators pour unimaginable energy into protons, pushing them ever closer to the boundary, yet never across it. We saw the prohibition sculpt the most extreme places in the cosmos. Black holes draw their horizons precisely where escape demands light speed, trapping everything within not out of malice, but as a direct consequence of the same rules that govern a flashlight beam. We followed the trail into the earliest universe, where inflation stretched space itself, carrying regions apart faster than light could travel through it, fragmenting the cosmos into isolated domains long before stars formed. We confronted the fate awaiting everything, accelerating expansion driven by dark energy, pushing galaxies beyond our horizon one by one, until our local cluster becomes the only island in an endless void, fading slowly toward heat death. We explored the quantum realm, where entanglement teases with instant correlations yet refuses to carry messages. We searched for loopholes, wormholes, warp drives, exotic matter, and found them closed by the same unbreakable logic that guards causality. We traced the fine-tuning, alter the speed of light even slightly, and atoms destabilize, stars burn wrong, chemistry fails. The prohibition sits at the center of the delicate balance that permits long stellar lifetimes, heavy element formation, planetary cooling, biological evolution, conscious reflection. We acknowledge the dark majority matter that shapes galaxies without shining, energy that repels without source, both obeying the limit while hiding from direct view. And through it all, we shifted perspective. The rule that seems to imprison us liberates us in unexpected ways. It enforces the scales needed for complexity to emerge slowly, safely. It protects causality, ensuring causes precede effects, histories accumulate, memories endure. It preserves mystery by maintaining distance. It transforms raw longing into refined contemplation. Because while matter is bound, light is free. Photons race across the cosmos unimpeded, carrying perfect records from places we can never reach. In catching them, we participate in the journey. Telescopes become our vessels, detectors our senses extended to the edge of time. We have watched galaxies born in the deep past, seen worlds forming around distant suns, read atmospheres for hints of life, all without leaving home. Future instruments will deepen this vision. Vast arrays resolving surface details on exoplanets, gravitational wave observatories hearing the universe's hidden vibrations, neutrino streams revealing stellar cores. We will map the full observable history just as acceleration begins to hide it forever. This timing feels like privilege. We inhabit the brief era when almost everything that ever happened remains visible. The prohibition grants us this complete view by setting the pace of expansion, the reach of horizons, the fidelity of signals. It ensures the universe remains legible long enough for minds to read it. And in reading, we fulfill a cosmic possibility. A fragment of the universe becomes aware of the whole. Matter assembled through billions of years of stellar alchemy gains the capacity to reconstruct those billions of years. Local beings comprehend global laws. Temporary creatures grasp eternal patterns. This emergence feels like the story's true climax. Not conquest of space, but conquest of understanding. Not spreading across galaxies, but gathering the galaxy's light into focused awareness. The prohibition makes this concentration possible by preventing dilution. No instant leaps, no premature mergers, no destabilizing paradoxes. It forces patience, cooperation across generations, humility before the vast. It turns science into a collective, long-term endeavor, knowledge passed forward like light itself. We stand on the shoulders of every observer who ever looked up, every experimenter who tested the rules, every theorist who followed evidence to uncomfortable conclusions. Their accumulated insight converges here in us now. And what have we learned? That the speed of light is not an inconvenience. It is the guardian of coherence, the enabler of complexity, the protector of solitude, the guarantor of discovery. It isolates bodies to connect minds through shared comprehension. It confines reach to expand vision. It draws boundaries to define meaning within them. The current scientific consensus is unambiguous. After more than a century of tests, from basement interferometers to orbiting telescopes, from particle colliders to cosmic surveys, no violation has appeared. Every observation fits the framework Einstein built from that single stubborn fact. Alternatives, variable speed theories, modified gravity, superluminal signals fail against the weight of evidence. The prohibition stands absolute, yet mysteries remain. What enforces it at the deepest level? Quantum entanglement networks, discrete spacetime, emergent invariance. Why this precise value, tuned so delicately for the universe we inhabit? What lies beyond our horizon? Other domains, other laws, other observers forever unknowable. Will quantum gravity reveal the prohibition as inevitable, or as one choice among possible realities? These questions do not diminish the achievement, they extend it. Because the universe has arranged itself through whatever mechanism to be not only habitable but intelligible, vast enough for wonder, structured enough for understanding, bounded enough for meaning, open enough for endless inquiry. We began asking whether the stars are forever out of reach. The answer is yes. And in that yes lies unexpected grace, because reaching was never the only way to touch. Seeing clearly from where we stand connects us more deeply than possession ever could. The light that left distant galaxies before Earth existed arrives here now, entering our eyes, sparking neurons assembled from elements forged in those same galaxies. The journey closes its circle. Stardust beholds the stars. Local minds encompass the cosmos. Temporary lives touch eternity through comprehension. This is the gift the prohibition grants. Not freedom of motion, but freedom of awareness. Not dominion over space, but intimacy with its laws. Not escape from limits, but transcendence within them. The universe is vast beyond imagining. Its distances are not punishments but protections. Its prohibitions are not cruelties but kindnesses. Its silences are not absences but invitations to look deeper, to listen longer, to understand more fully. We are small, fleeting, bound to one pale blue dot, yet in that smallness lies immensity. Because from this dot, the entire visible story unfolds. Because in these fleeting minds, the universe reflects upon itself. The prohibition that seemed to close doors has opened windows to everything. Our journey ends not with resignation, but with gratitude, for the light that reaches us, for the time granted to receive it, for the capacity to know. The stars remain forever distant. But in understanding why, we have come closer to them than any voyage could achieve. The universe is unbounded in its beauty. Its laws are precise in their mercy. Its mysteries are infinite in their welcome. And our awareness, fragile, local, luminous, is the rarest phenomenon it permits. We are here, we see. That is enough, that is everything. Thank you for traveling this path with me. The night sky waits, unchanged yet newly understood. Look up, the light is still coming, and we are ready to receive it.